it to the figure compared to quark density, gluon density goes very steeply for low values of X, and therefore top is basically produced by these kind of diagrams where gluons interact and produce the top. So without doing anything, you can learn so much from this simple one-line formula and help of simple arithmetic, that what kind of things you expect at the edges. And it also tells you that now if you talk about new particle searches, this mass itself is of the order of 1 TeV or so, then the earlier machines had very little chance, because then you will require very large values of x1 and x2 which are highly improbable, and they cannot go beyond 1 in any case. So we can forget about those things. Then what is very, very important is that by virtue of its huge center of mass energy, although the whole center of mass energy is not coming into picture, what is coming is x1, x2 times, yes, but just by virtue of having a large x, we can produce reasonable values of x1, x2 to create a heavy particle. We do not need absurd values of x1, x2 to create heavy particle. That is the beauty of the LHC machine, and the gluon flux, which is really large at low x, plays a huge role, but gluon flux of course is important only in producing strong interacting particles. For producing W and Z, they do not play much role, but they play a huge role. Now this is a little advanced, I mean the Feynman diagram is advanced.
The upper limit of the new particle mass.
How do you know? How do you know? What God created, how do we know? Well, what nature created. I don't like the word God created, although people call Higgs a God particle. Let us say what nature created, how do I know? If nature wants, it can create a gut particle, which is 10 to the 6. Now we will never be able to produce colloidal which will produce 10 to the 16 GeV particle. Sky is the limit. आसमान तो छूना है. If you really want to study nature, you may have to reach the sky. Sky is the limit, but it is not possible, at least with the present technology. But let me just tell you that this will give you another beauty. The Higgs is an electroweak particle. Right? Higgs boson is an electroweak particle. Higgs boson cannot be created from UB quark interaction. Technically there is a diagram which is, let us say for example, UU bar goes to the Higgs boson and then it will decay into something. The trouble is, although this diagram exists, those of you who know standard model, remember the coupling of Higgs with the quarks is always suppressed by a factor of mass of the quark divided by the mass of the drop. Now the U mass is a few MeV and the W mass is 80 GeV, and you are sunk at the very first stage. You cannot produce Higgs from quarks. Gone. So how do you produce Higgs? Well, one possibility of course is this UU bar will first produce, I cannot write down all the possibilities, so just two for comparison. Z boson, and then this Z boson radiates a Higgs, so to say, because there is a Higgs ZZ coupling. So this will be a typically electroweak process with small cross section, right? This is why most of the Higgs production cross sections look like needle in a haystack, because the total LHC cross section is dominated by the strong interactions, whereas this fellow is. But there is one process. This diagram is not a simple free-Weber diagram, as we say, but the thing is that dominant, there are other subdominant processes.
Excuse me, the second diagram.
Sorry?
Sorry, the second timeline diagram, possible or not? Each production, second timeline, U is what going to Z.
U is bar going to Z, Z going to this. Not possible.
Dominant or
No, why this is not possible?
yes.
U bar has a coupling with Z,
Yes.
and the pair of Z has a coupling with Higgs. One Z is virtual, one Z is real.
Yes.
Therefore it is possible.
Is it dominant mode of production?
That is what I am going to tell. The very fact that I have written subdominant, I called it subdominant and right here dominant, means that I am going to tell you the dominant production process. And that is peculiarly a higher order diagram. Maybe I represent the Higgs with a dotted line. And in this loop, you have the top one. Now, if the vertex is small, then a higher order diagram in perturbation theory is always suppressed. But not this fellow. This is very clever, because as I told you, this diagram will be proportional to this vertex, will be proportional to mt over mw. This is mt over mw, and this as well is mt over mw, and this is more than 2, so the product of 3 will give you an enhancement, although it will be suppressed by a factor of 8 pi square, which normally comes from the loop. But you have here the large so this is another reason why we had to wait for the Higgs production until LHC came into existence, because we never had a gluon machine before that. The highest machine that we had was the Fermilab Tevatron provider, but there the gluon flux gave about, I don't remember exactly, let us say roughly about 15% of the total cross section. Rest of it was quark, etc. But so there at the Fermilab Tevatron, this process was allowed, but this one was relatively small because the gluon flux was low. So that gives you another reason why we had to wait till the large hadron collider, simply because we didn't have a gluon machine before we had the LHC. LHC is a proton-proton machine, but by virtue of its huge center of mass energy, it virtually becomes a gluon machine, and therefore we could see the spectacular phenomenon of this gluon production. So Ranjit, what is the idea? You will take over now? We call for
tea break, 11.
when is tea break?
11:30.
11:30. Okay. Okay.
So then I have to cross little bit past 1.